Hey there. Let's take a look at the Unit 5 test review. All right, so in the first section, we have graphs of P of X represented with the solid curve and a set of data. Express the data as a function g in terms of P of X using function notation. So again, P of X is like the curve here. And then G is the set of data that we're trying to get it to match up to. So I noticed that this data and this curve have the same end behavior. I just need to do some translating. So it looks like we need to translate. If I kind of focus on, get my pencil going here. If I just kind of focus on this point here and then try and match it up to that one right there, then it looks like I'm going to be moving to the right by 1, 2, 3, and then up by 2. So that means g of x is equal to p of x. And then to the right 3, or sorry, wait, was it 3 or 4? 1, 2, 3. Yeah, 3. 3 and 2. Okay, so to the right 3 is x minus 3, and then up to plus 2 on the outside of the parentheses. All right. On the next one, this also looks like I can get there with a translation. So here's P of X, and then the data will be G of X. Okay. So, some points to focus on looks like this one right here. I can just move. Let's see here. Just trying to find a good point to use. This one right here actually looks like a good one on the orange. And then if I go to the right by 2 and up 1, I think it's going to match up just fine. So to the right 2 and up 1. So that means g of x is equal to p of x to the right 2 minus 2 and up 1 plus 1. All right, and then our last one, I notice we're going to need to do a reflection on this one. But to start with, I'm going to look at what's the movement, right? Because if we reflect over the x-axis, if we reflect function p over the x-axis, then it's going to look like this. And then I can focus on moving this point up here to this one. All right, so it looks like I'm going from 0, 0 up to 2, 5. So that's to the right by 2 and up by 5, and a reflection over the x-axis. So the reflection over the x-axis, that means we're going to be doing opposite outputs. So our negative sign for reflection will come before p of x. So g of x equals negative, again, because we're reflecting over the x-axis, so the negative comes first. P of x, it was to the right 2, so minus 2, and then up 5. All right. Okay, in the next set of exercises, we're just going to describe the transformations. So the function f and g are related. Describe a sequence of transformations that will take the graph of f to g. So what's happening to f here is we've got to shift to the right by 2 or translate right by 2 and reflect over x-axis. So remember those keywords not just translate, but what direction, left or right, up or down, and then reflection, but again, which axis are we reflecting over? So you can see here on the next one, we're going to reflect over the y-axis because we are doing opposite input. So that reflects over the y-axis. I'm going to go ahead and write that first. The y-axis. And then translate up by 1. All right. We can see here that we are going to reflect over the x-axis, but also we're also going to scale all of the outputs by 2 and then shift to the left by 1. So I'm going to start with what's in here. Translate left by 1. And then you can kind of, it doesn't matter the order of this reflection and stretch. They're both going to happen and they don't affect each other. So reflect. This is over the x-axis. Again, we're reflecting, or you can kind of think of the reflection is going to go on the output since it's on the outside. And so then that goes over the x because y's change from positive to negatives over the x-axis. So reflect over the x-axis, and this is a vertical stretch by 2. And then finally, we have a couple more things going on inside here. So we've got this scaling the inputs by 1/2, shifting to the left by 4, and down by 2. So I'm just going to write those all out. Scale the inputs by 1/2. And when that happens, it causes a horizontal stretch by 2. Remember, if something's going half the speed, then it takes twice the time. So that's why it stretches horizontally by 2 when it's being scaled. The inputs are being scaled by 1/2. Let's see, where am I? Okay, so translate left 4 and down 2. Okay. All right. Number 3 is a matching exercise. I'm going to focus on the equations and then bring them back to what's happening. So we spent some time looking at scaling the inputs versus scaling the outputs. And so when we scale this output by 3, that means that the distance is 3 times as far. And scaling the input by 1/2, that means the speed is half the speed. So it looks like B, the student is walking half the pace. So that would be the 1/2 and 3 times farther. So that would be the 3 there. So these match up. This is A of X. Okay. The next equation, now we're looking at half the distance. So this 1/2 out in front, that's changing the distance. And then 3 times the speed. So that looks like this one, half as far, but 3 times faster. And obviously the last two are going to match up, but let's talk about it. So this 3 in front of the outputs is going to change the distance. And then the 2 here connected to the input is going to double the speed, so twice as fast. So they match. Okay, and then write a new function d of x for a student who walks 5 times further and 1.5 times faster. So 5 times further, that's going to scale the output. 1.5 times faster, that will scale the input. So d of x equals 5, okay, of 1.5x. Okay. All right. Next is even, odd, or neither. So remember, even functions, you can see them on a graph. They reflect over the y-axis. So this one is even. On the next one, this is kind of that one exception. Remember how we talked about how odd functions go through 0, 0? Well, this is an odd function, but it's not going through 0, 0. However, its asymptotes are. And so if you think about, like if I were to put my little pencil right there and spin this 180 degrees, we have the same graph. So it has that 180 degree rotation about the, that 180 degree rotation about the origin. And you can think of it also as, if you reflect this over the y-axis, this will reflect over to here, and this will reflect over to here. And then if we reflect that over the x-axis, now this reflects down and we get our original graph on this side. And this reflects up and we get our original graph on that side. And so this is an odd function. Okay. And then finally, in even functions, the rule looks like this: f of x equals f of negative x. That means opposite inputs, x and negative x, have the same output. These are both positive. Okay. Opposite inputs have the same outputs. However, in odd functions, f of x equals negative f of negative x. And so opposite inputs have opposite outputs. And so if we look at, well, here's 0, 0. And then I notice positive numbers, 1, 2, 3, have positive outputs, 1, 8, 27. And then the corresponding negative numbers have negative outputs. So this table follows this rule where opposite inputs have opposite outputs. So this one is odd. All right, we've got a couple problems on the back side. Here we go. Okay, so we're going to talk about some meat that was taken out of the freezer to thaw. So 2 pieces of meat, both M of T and K of T modeled the temperature of the meat in Fahrenheit, T hours after it was taken out. So we've got M of T here and K of T here. It looks like they weren't taken out of the freezer at the same time. So if we just go through these here, describe the transformations that take M of T to K of T. So I noticed that this has a point at 0, 13, and this has a point at 5, 13. And so that tells me, oh, they weren't taken out, like I was saying. They weren't taken out at the same time. And it looks like K of T looks like that was taken out 5 hours whenever M of T was taken out. So the transformation to take m of t to k of t, we would have to move this to the right by 5. So translate. Write an expression for k of t in terms of m of t. So to get k of t, again, we have to translate m of t to the right by 5. So m of t minus 5. Okay, now Julie takes a package of meat out of the freezer, but puts it in the refrigerator so it thaws half as fast as m of t. Sketch the graph for Julie, j of t. So we're going to assume, it's not written here, but I think it's safe to assume that Julie's meat and the m of t meat were taken out at the same time, but Julie's is in the refrigerator, so it's thawing at half as fast. Okay, so that means we'd still have a point at 0.13, which is like here. But then I'm just going to look for another kind of good point. So here's 2 and 30, that point right there. So if it's going to thaw at half the speed, instead of 2 hours, that will take 4 hours to get to 30 degrees. So 1, 2, 3, 4, and then up to 30 degrees. And then let's find another good point, because not much is going to fit on this graph since we have to double. But let's see here, maybe 6. It's not too bad. So 6 is at about, I would say, 52. And so again, if I'm if something's happening half as fast, we have to double the time. So that would be 12, which is up here. And it's 30, 40, 50, about there. It would be 12:52. So this is still 0.13. And then this would be 4:30. And this would be 12:52. Okay, so it corresponds to those 3 points. And the difference is that the time is twice as long. So it kind of looks like this. And write an expression for j of t in terms of m of t. So j of t is equal to m of 1/2 t. Oops, put that up a little bit. All right. So at each point, 0, at each point, the time for m is half the time for j. So that's why the 1/2 goes right there. The time for m here is half the time for j. Okay, so the 1/2 goes right there. All right, couple of parabolas, couple of even odd functions, and we will be done. So, famous McDonald's golden arches are shaped like parabolas. One arch is 12 feet wide and 25 feet high. So we can label the points. So this would be 0, 0, 12 feet wide. So this is 12 and 0, and then 25 feet high. So I know that the y is 25 because that's the height. And then the x is 6, half of 12. All right. So find the quadratic function that models the arch height. So we know that we can use factors of x and x minus 12 because that's where the x-intercepts are. But we're going to need a k value. We need to scale this. So I'm going to write m of x equals some value k times x minus 12. Okay? And then I'm going to use this because I know when x is 6, the answer is supposed to be 25. So if I take my expression here and replace the x's with 6, the answer is supposed to be 25. Okay. And so, my calculator. So that means, let's see here. So I'm going to do, there we go. I'm going to do 6 times 6 minus 12, which is negative 36. Okay. So I know if this equals negative 36, then negative 36k equals 12. And so divide. So k. Oh, I don't know why I switched that to 12. I think I saw the 12. It should be 25. 25, sorry. Oh, I'm glad I caught that. Okay, so k is equal to negative 25 over 36, which I don't think is going to reduce. You can always check to see if something's going to reduce by, dividing, and then the math button, followed by enter and enter again. And look at that, it doesn't reduce. So my equation looks like this. It is 12. I keep switching the 25 and the 12 in my mind. I'm not sure why. There we go. Okay. And then we actually did this one in class, number 8, but I'm going to do it again, just kind of using this method. I think it streamlines a little bit easier, especially for those of you that like to set up and solve equations like I do. It's actually my favorite way of solving things. It makes so much sense. So the Gateway Arch in St. Louis is shaped like a parabola. The arch is 630 feet wide. So 0, 0, 630, 0, and 630 feet tall. So this is 630 is the y, and then 315 is half of 630. So that's the x. And then our equation. So again, m of x equals k times x for this x-intercept at 0 times x minus 630 for this intercept at 630. Again, I want to use the coordinates of this point. In the coordinates of this point, 315 is the x, so it's going to replace those x's. 630 is the y, so it's going to be like the answer, and then we can solve. So I know k times 315 times 315 minus 630 equals 630. All right, and so I kind of remember that answer, but I'm just going to double check. 315 times 315 minus 630 is, yes, negative 99,000. What? I did 631. Let's try it again. 315 times 315 minus 630. There we go. That's the number I remember. Negative 99,225K equals 630. So this step is a simplified form of that part of the equation there. This all simplifies to negative 99,225K. And so K is equal to 630 divided by negative 99,225. So 630 divided by negative 99,225 is a long decimal. So math, enter, enter, negative 2 over 315. Okay. So then the equation, m of x equals negative 2 over 315 times x minus 630. Okay. And finally, even, odd, or neither. Okay, so remember the rule for even functions, f of x equals f of negative x. So step 1, find f of negative x, or g. So g of negative x equals negative x squared plus 2 times negative x. Negative x squared is equal to x squared. And then 2 times negative x is negative 2x, which changes the plus to a minus. And so this is not the same as what we started with, so it's not even. So now we do a little check for odd. And to check for odd, we're going to do negative g of negative x. Put this in parentheses with a negative on the outside. So that means negative g of negative x equals, when I distribute, I get negative x squared, negative, so plus 2x. This is also not what I started with, and I tried both rules. So it's not even, it's not odd, it is neither. All right, the next one. We always start this the same way. H of negative x is equal to negative x to the third minus 2 times negative x. Excuse me. So negative x to the third, because our exponent is odd, this is the same as negative x to the third without parentheses. And then minus 2 times negative x becomes plus 2x. It's not even because those are not the same. So we check for odd. Oh, I don't know why I did those parentheses. It doesn't change anything, but they didn't need to be there. And so we have negative h of negative x, and then distribute this negative. So that just changes the signs. So this becomes positive x to the third and minus 2x. Now, this is what we started with. And so I can say, oh, h of x, not f of x. H of x is equal to negative h of negative x, and so it is odd. All right. And then finally, j of x. So we're going to check j of negative x. It already has a negative sign there, so I'm going to leave it on the outside. Negative x on the inside, squared plus 10. Okay, so I have to ignore this for just a moment, and because it is not connected to the power of 2. The power of 2 is only for negative x, and negative x times negative x is positive x. So then when I make it negative, it's going to go back to negative x squared. And then the plus 10 is not affected because it didn't have its sign changed. It doesn't have a variable on it. So I rewrote and simplified, and this is what we started with. So since j of x equals j of negative x, this function is even. All right, that is the end of the review. Happy studying and good luck on your test.